Hi guys, in this video I want to piece together some of the pieces of standing waves. I've explored some of this hopefully with you in class, and I kind of want to put it all together to motivate the mathematics, to show why the mathematics is kind of beautiful, and then show you the mathematics at the end. So that's where we're going. Shout out to XM Demo. He's a teacher in, I want to say Singapore, and he's recorded some awesome demos, and I'm going to show you this one of a standing wave. So it's just a metal slinky attached to this end, and he cut it really nice. Let's watch. This is the second pattern. N stands for node, A for antinode. This is the third pattern. Fifth. Sixth. Seventh, you can count them. And eighth. Those are the patterns. Now the question is, why? What's giving rise to that? Again, this is something that I hope I've explored with you in class. When I'm thinking about it, I'm really thinking about this simulation right here. It kind of slows things down. When you have an incoming wave at a boundary, it's going to reflect and reflect inverted. And when it reflects, when two waves sort of overlap, they interfere with each other. When they're sort of out of phase, you have a wave kind of on the bottom and a pulse up top. When they add together, they're sort of canceling out. So when they're fully overlapped, what you're seeing in the black dots is what you would see in the string. So at this snapshot, they're completely canceling out. A moment later, they're now adding together. This pulse and the one behind the original, they are adding together. And if I was to step it further, they're completely overlapping now. And now they're kind of canceling out. Here they're adding together, and here they're canceling out. So if you zoom in on, let's say, this spot K, notice that those waves are always canceling out at K. So that's what makes it appear like the wave is standing still at those points. It's almost like there's no wave going through, but really there's a lot of constructive and destructive interference happening, rather just destructive at that point. If you zoom in at point P, or B rather, here they're completely adding together. A moment later, they're starting to cancel out. Then add together, then cancel out. So there are points along this medium, along this, in this case, the string, where there is consistent constructive interference and consistent destructive interference. And as the waves move, the points of constructive interference kind of vary. Sometimes they completely add together, max height, and then sometimes they are sort of canceling out. So it's literally waving in place. What I also want to highlight, though, is nicely shown in this pivot interactive video. So over here you have a speaker attached to a string. The string is taut because there's this mass hanging on it. And what I like about this video is that it shows not just the standing wave patterns, but what you see over here is the frequency that the speaker is driving at. So over here it goes kind of quick. This is about 10 hertz, where you're seeing this first pattern. But then as you keep increasing it, right here we're about 15 or 17 hertz. There's no pattern. I'm going to rewind just a little bit. So pattern, you see the first pattern, and then there's all these frequencies in between where you're not seeing it. And then the second pattern emerges. Right around 20. No pattern. And then right around 30, another standing wave pattern emerges. And no pattern. And then around 40, you're seeing another standing wave pattern. So I'm hoping you're seeing some pattern here, like, hey, the standing wave patterns come in specific frequencies only. They're really special in that when you have a medium of, let's say, a certain length, and when the waves travel through at a certain speed, only specific frequencies, when you're driving the wave at specific frequencies, only that will cause the standing wave pattern to emerge. Those waves have to have certain wavelengths. You could also equivalently think of it in terms of frequency. The other thing I wanted to just share with you is if you've ever looked at the frequencies of notes on a piano. So they repeat. You have an octave C, a higher octave C, and then a higher octave C. Hopefully I shared this with you. But if you, basically as you go from C to C, there's a pattern in the frequencies. And I can sort the notes. So I don't know if you can see it, but those are mathematically related. They're intervals of each other. So double this, double that, double that. There's this nice pattern that emerges when you look at the frequencies. And we can kind of understand why those frequencies are sort of chosen as notes, and why only certain frequencies emerge when you have a length of string attached at two ends when we look at the mathematics. The mathematics kind of gives us a nice, beautiful equation that helps us predict and understand this. Okay, so the basic idea, standing wave patterns, there's a pattern to the frequencies. Only certain frequencies give rise to those patterns. So what is the pattern in the frequencies? Let's look at a string of length L that's sort of nailed down, fixed at both ends. And I'm going to look at the first 5 standing wave patterns. So what are we trying to do here? We're trying to get an equation for the frequencies that are allowed on these strings of length L. So something you can do, you can pause the video and try to draw what are the patterns. What do they look like, number one? Oh, I said I'd only do 5. So let's get rid of this one. Space. What we're trying to get is an equation for lambda in terms of n, where there's the first pattern, second pattern, third pattern, fourth pattern, and fifth. And then ultimately what we really want is an equation for the frequencies in terms of these patterns. Okay, so let's get into it. The first pattern. Boom. The simplest one. The second pattern. Boom. The third pattern. I refer you to XM Demo's video if you don't believe me that those are the patterns, but like the simplest one is this one. This is the one that comes at the lowest frequency, and then this one, and then this one. The fourth one is like this, and the fifth one looks like that. It should be more even. Let me see if I can do a better job with that. Still not the best, but you get the idea. Also, these things are, sort of waving up and down. So that's why I'm drawing these dotted lines in here. I want to remind you that the points that are sort of fixed and not moving, we call those the nodes. Like here on the ends. And the points that are of maximum displacement, those are called the antinodes. So now the next part of this is those are what the patterns look like. Can you relate the wavelengths to that length L? So what is the wavelength of this wave? Well, one way to look at it is that, hey, if you were to see the full wave, it would look like this. And so one wavelength is about 2L. That'd be one way to do it. A more suggestive way to look at this is this distance right here. This is a half wavelength. And right now I have that L is equal to 1 half wavelength. How many half wavelengths do I have here? I have 1, 2. So this right here is 2 half wavelengths. 1, 2, 3. This one is 3 half wavelengths. This right here is 1, 2, 3, 4. L is equal to 4 half wavelengths. And you guessed it, 5 half wavelengths. So if I was to write this equation in terms of n, do you see what the equation is? I basically replace this number, the number of the pattern, with n, so that I have L is equal to n lambda over 2. And if I'm to rewrite this in terms of lambda, that's lambda is equal to 2L divided by n. What am I really driving towards, though? I want those frequencies. So how do I relate lambda to frequency? Because like when we're talking about music, you tend to talk in terms of frequencies. So V equals F lambda is how I can relate them. V is the speed of the wave through your medium. And when it comes to sound, the speed of sound through air is about 330 meters per second, about 600 miles per hour. And that only depends on the medium itself. So when the temperature goes up, the speed of sound changes a little bit. If you were looking at sound traveling through water, it would be at a different speed. So this is like a constant. The speed through the medium is a constant, and it depends on the medium itself. So when it comes to a string, sort of the density of the string, how dense it is, and the length. So the density and the tension it's under. That would sort of be the two factors that affect the speed of the wave through that. That's a separate issue. Okay, so combining our equation for wavelength with this equation will give us V is equal to F lambda n. F is equal to V divided by lambda n. And then finally, Fn is equal to V divided by, this equation, 2L over n. So what my final equation is, n times V over 2L. Boom. I'm going to unpack this equation on the next slide. N V over 2L. So let's get some intuition for this. When n is equal to 1, the frequency is V over 2L. Again, V is just some constant, and L depends on, hey, what's the length of the string. If n is equal to 2 times V over 2L. Sorry, that's supposed to be 2. Two times V over 2L. But hey, this is my fundamental frequency. So then the frequency of the next harmonic, the second pattern that emerges, the second harmonic is what we call it, is just 2 times the first frequency. And F3 is going to be just 3 times that first frequency. And that's why we call this one the fundamental, because it's related to the ones that pop up. The higher harmonics are just multiples of that fundamental. And so that's kind of where the mathematics of choosing specific notes comes from. There's other things involved as to like what frequencies you hear more in certain instruments. Hint, hint, it's not just the fundamental when you, let's say, hit a guitar string. There's other frequencies involved, and it's related to this. But that's a topic for another video. To summarize, what causes standing waves? Vibrating a medium at specific frequencies, and those frequencies depend on the speed of the wave through that medium and the boundary conditions, or the length of the string in this case. Hope that was helpful. Take care.